Sure. So my name is Siddhartha Dash, or Sid Dash for ease of pronunciation and simplicity. I work for Chartis Research, and Chartis Research is essentially a research firm focused on risk analytics and compliance technology. So we look at the whole landscape of risk analytics and compliance and their underlying technologies. So we look at the technology and the risk crossover, of, if you will. So at this point, I guess I have an accountability to ensure that you guys finish at 5. That's number one. And number two is I think Michael did a great job of talking about the, the what and the what do you want to do in your risk management framework? What do you want to do in your, and how do you go around building it and so on and so forth. I'm going to actually concentrate on something slightly different and somewhat orthogonal to that, if you will. I'm going to concentrate on the idea that the available technology today is actually in some ways outrun its utilization. The technologies there are a range of technologies, which things like object databases, graph databases, domain-specific languages, and a range of other things, which we will talk about a little bit as we go along, which have enormous application in risk generally and GRC specifically. And we'll see that many of this is perhaps not being utilized as much as possible. Equally, before this, we heard a discussion about CRQ, and and that was fairly interesting, and that sort of focused on a CRQ simulation framework. And again, the issue was, where is the data? And we'll make the case that that in many aspects of GRC modeling, GRC analytics, and operational risk modeling, the situation has changed today from the past where you had very little data to a situation where you have way too much data. And the challenges are really of handling way too much data, and how can you handle it using appropriate technology, rather than the challenge of the fact that you didn't have data at all. And I think the real issue is to look at these problems somewhat differently. And if you look at them differently, you certainly find the same problem has either the technology is available, or we have way too much data, or the data environment is something more easy to handle. So we just call this GRC plus to borrow Michael's definition. The idea is here, I'm not going to define GRC, but what I really mean here is that today we're in an environment where every aspect of that governance, risk, and control environment actually has available technology to solve it. We'll go through some areas, for example, like the data issues. We'll go through some areas like the data, like the domain-specific language issues, and we'll see that we are in some ways in an environment where the applicable technology has been proven in some part, and just talking about financial institutions, the applicable technology has been proven in some part of the financial organization. If you think about low latency technologies, we know they have been proven in the low latency trading environments. If we think about NLP technologies, we know they have been proven in many aspects of the compliance area when you are looking to do sanction screening and things like that. So the idea that I want to bring, the thesis that I want to talk about today, and I want to go through very quickly, if you will, is that for most of GRC problems, we have available technology, and I want to give you examples of some of them as we go along. Before we get to that, the first thing is our central view is that enterprise control requires enterprise solutions, and there are a range of different areas. I mean, whether we are thinking about IT risk, privacy risk, or the core risk and compliance areas, operational risk, or business-specific lines of control, we think we have come to a point where if I think about the operating technologies that are present in most banks, we can actually automate. We can automate control libraries. We can integrate control libraries into pre-existing technologies. For example, if you think about end user computing controls. There's a universe of spreadsheets everywhere, and one can despair and give up. But there's also a whole range of spreadsheet control technologies available out there. And they range from fairly simple models, which will scan and find all spreadsheets in your network, to more complex models, which will scan and find more spreadsheets, provide control breaks on your spreadsheets, and then go further into even converting your spreadsheets into C++ or any target language code. So again, I will emphasize the sort of maturity of compiler technology to enable a range of activities, automation and control activities that you see here. And this is really what is interesting from our perspective. As an organization, Chartist, we look at literally hundreds, or if not more, thousands of institutions and their operational practices. And one of the things that we've observed is the wide variety in levels of maturity. And again, just borrowing, and in most tier one institutions, it's wide variety within those institutions themselves in levels of control. Automatic controls in some parts of the business and zero automatic controls in other parts of the business. Ability to handle very complex VLDBs, very large databases in one part of the business, and no similar ability to handle that in other parts of the business. Just learning from within your organization, there's a lot of technology that you can actually pick up and expand. And I think that's in many ways our central theme. The other thing that we actually talked a little bit about, and I think there's been several discussion points so far, is the issue about how do you handle things like cyber risk quantification, et cetera, all of which are highly dependent on the amount of data available. And our central thesis today is that in most organizations, with very few exceptions today, you actually have ability to monitor every transaction because every workflow has an electronic trace. Every workflow has an electronic trace. So you can actually look at your network in real time. There are also a range of applications, for example, and I'm going to illustrate it just with the cyber risk quantification sort of model, if you will. There's a range of applications that can actually look at millions of internet endpoints at the same time. So if you recall, for example, one of the quantification tools that is currently held by ISS, which is a unit of Deutsche Börse, it actually looks at 2 million odd internet endpoints, captures the data at every 10-second interval, and holds that state of the internet landscape, if you will, that snapshot, which it uses machine learning to analyze and provide a cyber risk score of possible cyber incident by industry class, by all those 2 million odd firms. I mean, actually, those 2 million firms are not 2 million firms, because a single firm like Citibank may have 1,000 endpoints and so on. You need to consolidate it to individual firms. But they do provide quite helpfully individual firms, individual indexes, so you can have all the pharmaceutical firms and you can find their score. You'll find a score that ranges between 300 to 800, like the FICO score, which is no surprise because this was built at the time. This was at one point FICO's cyber score, if you will. But the point is not the cyber score. The point is that it's possible to monitor the entire 2 million odd landscapes with standard VLDBs that are available in the market. And that is our central thesis, that when we say we don't have enough data points, that's not true. We have enough data points. Similarly, if you revert back and think about IT risk, or you think about cyber risk within the organization, then your IBM technology management systems, or ServiceNow, or any other technology control system or incident management system monitors every workflow and every process at a given point in time. So you have a snapshot of your network state at every given second, or perhaps maybe 10 seconds at any given point in time. So the idea that we don't have data is in our view highly inaccurate. There are examples we have seen where due to digitalization, the data is entirely available. You can monitor every API. You can create a snapshot of every API at every given, within whatever is your control environment, 10 seconds, 5 seconds, et cetera, et cetera. So first and foremost, the thesis here is data is a monitorable, and you can actually store it. There's a range of database infrastructures which can store data very cheaply. InterSystems Cache, DDN, many others can store little, and their open source equivalents can store that data quite relatively cheaply. They're all available. They're all used in financial services infrastructure. So we're not recommending technologies that are extremely exotic or not available. So So moving forward, our central point is that we now have an environment where, and I'm going to look at 4 or 5 specific technology types. We have an environment where our standard operations and processes are now very tightly interact and can be leveraged using specific technology environments. We think about big data as essentially large data lake type environments, but also we have to think about other types of big data environments, which are, for example, object-oriented databases, which can allow you to store complex structures in large data sets. As I said, I gave an example. InterSystems Cache is an example of that. It's been used in many of the low latency trading environments. It's been used to hold large structured data sets as well. Document data, document data that supports trading environments. It also has been used in the energy systems environment to hold asset universes, to look at the full asset environment, the spatial location of energy assets, and so on and so forth. All of which are extremely data intensive applications, which when you look at the raw data that it stores and holds per unit cost, it is incredibly competitive and would easily handle any regulatory process data from a sheer size perspective. The second element which is incredibly lightly used in our context is hardware accelerated databases. Hardware accelerated databases and hardware accelerated infrastructures, for example, that leverage either the GPU or the FPGA, are one of very thinly used we see in GRC situations. But the great advantage of using something like an FPGA database is you can customize your exact query. We heard of people trying to use knowledge graphs. So you could map a knowledge graph to the FPGA environment, and that would ensure that your performance is at probably the highest possible level, and preserves the flexibility that particular knowledge graph structure requires. As you know, knowledge graphs are fundamentally only as good as the knowledge graph model can be built around. Similarly, we've seen the ability to create new domain-specific languages. Rapid growth in compiler technology has now allowed you to create very structured and specific languages. For example, the language could be focused on handling networks. So network could be a minimum element of that whole of the language, the core construct, just like there are domain-specific languages in marketplace where you see them focused on cash flow and payments and similar structures. The payoff languages are a pretty standard part of market and credit risk. particularly market risk and market link risk, and that can be easily mapped to.
He wrote it in the report.
We've spoken a little bit about object and NoSQL databases, but again, the variety and diversity of database availability today is extraordinary. If you remember, there are easily more than 400, several hundred types of databases available today. And when you think about even graph databases, which can potentially encapsulate things like knowledge graphs, etc. There are at least 15 and 20 types. The Tiger graph and the Neo4js are hugely different from each other in their encapsulation and so forth. And finally, workflow and orchestration engines. Again, there's a variety of options available. You can encode your own, perhaps using languages like Lua. So centrally, what we are really saying here is every aspect of what we think as a traditional GRC process or data analysis process now has a technology which is reasonably widely available in the financial services universe and can be leveraged. We've seen examples of this in a variety of GRC style problems, and we think again our central thesis is the technology has run ahead in some ways of the application, and now what it requires is a little bit of clever application, bringing it back to the problem in question. With that, I close, and with that, I fundamentally close, and we'll leave you with the final thought that we think there is this need to industrialize the development process, the DevOps and model of validation and model analysis operations, and we think that's the next future path. That close.
Okay, before you close it, are there any questions for Sid in 1 minute? There is.
Because it's all over.
Thank you, sir, for very informative presentation. Do you believe there's a role of blockchain in GRC?
My answer is probably no.
Okay.
But I mean, surely GRC is such a large universe. There may be one, but it's very difficult to see given the cost of reconciliation. I mean, blockchain's single biggest map, as we see it, is reconciliation type exercises. The cost of reconciliation is essentially moving down to zero, given the nature of databases. It seems very hard to see why there isn't an alternative. So our answer would be yes, we can see many potential use cases, but the cost of reconciliation and matching is moving down to literally zero. And in that economic environment, it's very hard to see how a more complex, immutable type style framework is actually going to be economically better than cheaper alternatives, if you will.
All right, thanks.
Great, thank you very much, Sid.